No worries. So we have just started recording this presentation of our weekly Research School of Earth Sciences seminar series. I'd like to acknowledge that the seminar series, at least at ANU, is meeting on Ngunnawal Ngambri land, and acknowledge the custodians of that land, past, present and emerging. We've just been talking about how it's a rainy day here on Ngunnawal and Ngambri country, but the sun is shining in Wurundjeri country, which is where Elisabeth joins us today from Melbourne. She's based at Monash University, as you can see on her opening slide here. And you might get the impression that Elisabeth works on accessory minerals, and in fact she does. And so Titanite is a minor or accessory mineral in many kinds of metamorphic and igneous rocks. Elisabeth did her PhD at the University of Western Australia on these kinds of minerals, finishing in 2018. She then had a very short postdoc and went off into industry, working for 2 years with ESO. And she's told me that she's really enjoyed coming back and doing a postdoc at Monash, which she started 2 years ago. She has worked during that time on a whole range of different topics, mostly related to looking at orogenic histories of multiple areas. So using geochronology, thermochronology and isotope geochemistry to understand the timing of orogenic processes. And it sounds like she's going to tell us more about that today. So Elisabeth, welcome to the virtual Zoom room, and we'll look forward to hearing your talk today.
Thanks. Yeah, thanks, Penny, for that lovely introduction. So yeah, one of the things that I'm most interested in is how we can basically make better use of the information that's stored in accessory minerals. And there are a lot of different accessory minerals, and a lot of them have been receiving a lot more attention in the last few years. So things like apatite, monazite, rutile, and so forth. Today, I'm here to talk to you about titanite. And to that end, I've been developing some tools using simple machine learning techniques with a large compiled data set to help geochronologists to better understand the age and the compositional data that they get from titanite. But before I get stuck into that, I'm just going to give you a quick roadmap for my talk today. So we'll start with why zircon isn't the answer to every problem. And then we'll talk about some of the characteristics of titanite that make it so useful. Then I'll talk about the data compilation that I put together. We all had to do something during the COVID lockdowns. That's what I did. And then I'm going to show you some of the geochemical indicators that I've been able to derive from that data set. And then finally, we'll finish with a couple of examples of how these tools can be applied to real rocks. Okay, so let's start with a couple of hypothetical scenarios that provide the motivation for this work. So imagine that you've got a mineral age from a metamorphic rock. It could be almost any accessory mineral. So zircon, titanite, rutile, apatite. We can date all kinds of things these days. So you've dated your mineral and you get a number. But what does that age actually mean? And how does that relate to the metamorphic history of the rock? This can be complicated by things like multiple orogenic cycles, high-grade deformation, maybe there's been exhumation, maybe there's a low-grade or a retrograde overprint. And then you might also want to ask yourself, how does this mineral age relate to other minerals in that rock? So things like garnet, which is one of those perennially useful minerals for telling you about your metamorphic PT conditions. Maybe you don't work on metamorphic rocks. Maybe you work on detrital sediments instead. And so imagine that you've collected some mineral ages from a detrital sediment sample. Again, you can date all kinds of minerals. But here is one example from the literature where this person has analysed titanite, rutile and zircon from a modern river sediment. And so they've dated these minerals, and so now you know that there are rocks of about these ages in the source region. So you've got age peaks at around 900 MA, 1400 MA and 1600 MA. Okay, cool. But what was the protolith? Was it a granite or a granulite? And so do these minerals tell you about magmatism or about metamorphism in the source region, or maybe a different process altogether? And so these kinds of questions about how to interpret geochronological data are absolutely fundamental to the geosciences. And if you've worked with any age data at all, you've probably grappled with these questions. So one of the ways of tackling this is through petrochronology. And to my mind, this is one of those examples where someone's invented a new word to describe something that people have actually probably been doing for a really long time without needing any particularly special name for it. Petrochronology really just refers to using additional information, trace element information, to interpret isotopic data. So for example, you might take your titanite uranium lead data and then combine that with petrographic information about mineral zonation, and then combine that with your trace element data and put that together to help you interpret what the age data actually mean. This approach to understanding geochronology has really taken off in the last decade or so, along with the rise of split stream laser ablation ICP-MS techniques, because this basically means that you can now extract isotopic data and trace element data from the same volume of material, rather than having to analyze them separately from different spots. Now, historically, a lot of this kind of petrochronology, as well as just geochronology in general, has made use of zircon. And there's a really good reason for that. Zircon is useful primarily because it is so robust. So it crystallizes at high temperatures, and it can survive high-grade metamorphism and several sedimentary cycles of erosion and deposition more or less intact, all while retaining its geochronological information. In fact, the Detrital zircon record provides an invaluable record of the episodic nature of Earth's history and of the supercontinent cycle. And this is just one Detrital zircon compilation here. There are many in the published literature. However, as with anything in life, the strengths and the weaknesses are two sides of the same coin. So if you look at things from another perspective, you might have a different view. So zircon is primarily an igneous mineral, and it primarily crystallizes at high temperatures. And it also primarily appears in felsic compositions rather than mafic ones. It doesn't always record metamorphic processes, particularly if the metamorphic grade isn't high enough. And so we know that if we only look at zircon, this won't provide a complete picture of the crustal record. So here's another example of here's another version of the Detrital zircon record in purple, and this is plotted together with the Detrital monazite record in green. And you can see that while there are a lot of similarities between these, there are also some differences. And understanding those differences can tell us something about the geological processes at play. So whether you're working at the small scale, trying to understand just one sample's history, or whether you're working at a much larger scale, looking at global processes, there's just a lot of information that isn't captured in the zircon record. And this is where other accessory phases like rutile, apatite, and what I'm going to talk about today, titanite, really come into play. So these minerals crystallize in a different range of lithologies, sometimes at lower temperatures than zircon, and they can also record metamorphic processes that zircon might not record. Okay, let's talk about titanite. So titanite's a calcium titanium silicate mineral, formerly called sphene. So you'll probably see that in old papers. It went an identity change sometime in the 80s and has been called titanite since then. It's a common accessory mineral in a wide range of lithologies. And so you can find it in all kinds of things, from felsic igneous rocks, sometimes in some more mafic compositions, depending on things like calcium and aluminium content. Metamorphic titanite, so titanite in metamorphic rocks tends to be stable at moderate pressure and temperature conditions, sort of ranging from upper grain schist to the upper granulite facies, the lower granulite facies. So it'll appear in rocks like amphibolites, orthogneisses, some polite compositions, and calc-silicate rocks. And titanite is also a common hydrothermal or alteration mineral, where it's sometimes associated with skarn deposits. As we saw earlier, titanite is also reasonably robust to weathering and to sedimentary transport. So there's a good potential for its use in detrital sedimentary settings. So I showed you this example on the very first slide. And you can see here that the Titanite preserves both the older and the younger components of the age signature, which are also seen in the rutile and the zircon. Now, because Titanite is one of several minerals in a rock that can contain titanium and calcium, it can actually be very reactive during metamorphism. And this can make it quite susceptible to recrystallization. And so this produces quite common zoning in Titanite. And these zones then will record a range of geological processes. So things like changes in pressure, changes in temperature, changes in bulk rock composition during the crystallization of that Titanite. And these are then accompanied by changes in trace element composition. All right. So yeah, one of the other reasons that Titanite is so useful is because it can incorporate a wide range of trace elements into its crystal structure. So this figure here shows Titanite melt partition coefficients for a range of elements. And I'm just going to race through a few of the highlights here. So this figure is derived for Titanite crystallizing from a single melt composition. But the main point here is that Titanite can take up all kinds of things into its crystal lattice. So, and for reference, this is titanium here, the partition coefficient, and this is a formula element in Titanite. So Titanite's a major repository for the rare earth elements. It's also one of those strange minerals that actually slightly prefers the middle rare earth elements compared to the light or the heavy rare earths. It also incorporates the high field strength elements, which is shown here in pink. In fact, the zirconium content of Titanite is temperature dependent. Excuse me. And it has been calibrated as a thermometer, which is useful for obvious reasons. So, for example, here, in this paper, the authors used the zirconium thermometer in Titanite in conjunction with the uranium-lead age to determine the thermal evolution of southern New Zealand. Titanite can also incorporate some other elements, things like strontium, vanadium, scandium. It also incorporates uranium in the tens to the hundreds of ppm, so it substitutes for calcium in the crystal lattice. And this means that it can be dated by uranium-lead geochronology, which is good news for us. Although, unfortunately, Titanite also likes to incorporate significant amounts of common lead. And so this is something that needs to be corrected for during the data reduction. Okay, so that's a long list of trace elements. Like I said, the main point here is just that Titanite can incorporate a wide range of trace elements. Okay, and so when we think about what this actually means and the sorts of work that has been done with other accessory mineral geochronometers, we can see that there are actually a lot of really useful trace element-based indicators that exist. So here are two examples where the trace elements content of rutile and apatite can be used to discriminate between different host rock protoliths. But for Titanite, there's nothing like this really exists yet. So most studies to date of Titanite tend to focus on a small set of samples. And these typically involve just a limited range of host rock compositions, sort of because of the nature of the study. But really, there's been enough publications now that we can start to put these together and look for some more broadly applicable geochemical indicators. And so I was really inspired by this kind of work in other accessory minerals when I set out to try to find some useful petrogenetic indicators in Titanite. Okay. So I mentioned the data compilation. And so to this end, basically, I put together a data compilation of published laser ablation ICP-MS trace element analyses of Titanite. I really tried to aim for a representative data set, so Titanite from different lithologies, different geological settings. Interestingly, we found that the most commonly measured elements are the rare earth elements and uranium and lead, so the geochronological elements. Other elements, while useful for geochemical discriminators, so things like aluminium and iron, they were actually much more inconsistently measured between different studies. And so that made things a little bit difficult because sometimes there are these really nice, large data sets, but because they didn't analyze a really useful element, you can't really add that to the compilation. Another thing in the compilation was just making sure to add all the metadata. So this is things like the lithology, the mineral assemblage, and anything the authors said about the paragenesis of that titanite. So specifically, we classified them according to the igneous and metamorphic origin, according to bulk rock composition and metamorphic grade. And in the end, this resulted in just over 7,000 analyses in the compilation. Okay, and so here's a brief summary of the types of data that are in that compilation. And I'm just going to state up front some of the limitations of this data set. So first, as you can see, the data are pretty heavily skewed towards metamorphic rocks. And this really represents what has been published, what analyses of titanite have been published. So as we've already seen, titanite is quite common in metamorphic rocks, and it's also a good chronometer for metamorphism. So that's just what a lot of studies seem to be paying attention to. I think that's just what the community is analysing. I also want to point out that the study doesn't include any titanite from hydrothermal rocks, so things like skarns, because the effects of fluids really complicate things. And then also due to just a lack of publications, the data set doesn't contain many samples from Archean rocks. However, when we break this down by bulk rock composition, we can see there's actually a good number of analyses in all the different categories. And so these all come from a large number of unique samples as well. So it's not just like one sample with a bunch of analyses. So I think the compilation is pretty representative with respect to igneous and metamorphic origin and with respect to bulk rock composition. Even igneous mafic titanites, which is the smallest category, has nearly 250 individual analyses from several unique samples in several different studies. Okay, so we've got a large data set. So what do we do now? Well, now the hunt is on. So we're going to try to find some patterns and try to find some useful geochemical indicators. And there are a lot of potentially useful things to look into, but for today, I'm just going to talk about these three. So looking for a garnet signature, igneous and metamorphic titanite, and looking at the host rock composition. Now, you might remember from other minerals and other branches of geology that garnet's a major repository for the heavy rare earth elements in a rock. And frequently or commonly, after garnet crystallizes, there are less heavy rare earth elements available for other minerals that might appear later. And so we can link depletion in heavy rare earth elements in a mineral to crystallization in the garnet-bearing assemblage. It works for zircon, and it also works for monazite and other accessory minerals as well. So let's have a look at whether it holds up for titanite in this data compilation as well. And so just one quick note here. There are a lot of different ways to measure depletion of the heavy rare earths. I'm going to be using the dysprosium to terbium ratio. The gadolinium-lutetium ratio is also pretty common. Dysprosium to terbium just seems to work best empirically for titanite, and so that's what I went with. So the higher the ratio, the higher the number, the greater the depletion in the heavy rare earths. Okay, and I'm sure no one will be surprised to hear that, in fact, it does seem to work for the titanite in our large data compilation. So starting with a more sort of a qualitative approach, you can see that there just is a difference in the heavy rare earth depletion between the two populations of titanite. So in fact, about 3/4 of titanites in a garnet-bearing assemblage have a dysprosium to terbium ratios greater than 2, and about 3/4 of titanite in a garnet-free assemblage have dysprosium to terbium ratios less than 2. But as you can see, there is quite a lot of overlap in these distributions. So there's a lot of titanite from garnet-bearing assemblages that hasn't got this signature of heavy rare earth depletion. And why is that? Well, I think there's a few reasons, but basically it sort of comes down to the fact that this simple metric of garnet-bearing, garnet-free doesn't take into account things like the abundance of garnet in a rock, the bulk rock composition, or the timing of titanite crystallization relative to garnet. So whether titanite crystallized early or whether it crystallized late. And all of those would have an impact on the heavy rare earth available to titanite. Yeah, and we'll talk a bit more about that later. But overall, this is great news because basically the data are doing exactly what we would expect them to. Okay, so now let's see if we can make this discrimination a bit more robust so that it becomes useful in a forward modeling sense. for samples where you don't have petrographic context. And so where you can't just look at the rock to see if it contains garnet. So things like detrital minerals. So this is basically a one-dimensional modeling problem. You've got one variable, which is the dysprosium to terbium ratio, and you've got a binary classification, so garnet-bearing or garnet-free assemblage. And so for a classification problem like this, a good choice of algorithm is a logistic regression. So what this does is that based on the distribution of the input data, it uses a sigma function to predict the probability of any given data point belonging to one of the two groups. So in a graph, it looks like this. So the x-axis is the dysprosium to terbium ratio, the y-axis is the probability that the sample crystallized in an assemblage that contains garnet. So for low values of the dysprosium to terbium ratio, the predicted probability is close to 0. For high values, the predicted probability is correspondingly high and somewhere in the middle. So particularly for values between, say, 1 to 4, the probability is more intermediate. One benefit of using this kind of regression approach is that you can use part of your data to define the boundary between categories, and then you can test how good it is at classifying the data with the rest of your data set. So this logistic regression was trained on 75% of the compilation data set. And when it was tested on the remaining quarter of the compilation, it correctly classified 73% of titanites from the garnet-bearing rocks and 81% of titanite from the garnet-free rocks, which is pretty good for a start and is certainly better than guessing, which is 50-50 chance. So, and I just want to note as well that it makes sense that there's more misclassification of titanite from the garnet-bearing rocks because of the wider range of dysprosium to terbium ratios from that group. Okay, so let's look at our first case study to see how this might be helpful. So this is basically looking at constraining the timing of metamorphic garnet growth in the Albany-Fraser origin of Western Australia. So we'll start with this sample, which is a pollutic gneiss, and this is just an image of the thin section. And you can see that it contains these nice large garnets, which have this schistose foliation that wraps around them. There's titanite present both as inclusions within garnet and within the matrix in the sample. Titanite is zoned in backscatter electron images. So it's either got this nice core rim zoning or it's got patchy zoning that follows the subgrain boundaries and cracks. And these different morphologies correspond with different trace element compositions. So most of the titanite, the analyses with titanite in the matrix and the rims of the zone grains had these hump-shaped rare earth patterns in the orange color in the background, with the depleted light rare earths and depleted heavy rare earths. But the cores of the zone grains and some of the inclusions in garnet had these much more flat rare earth patterns. And if we apply our logistic regression to these data, we see that the cores of the zone grains, so the blue dots, typically have a low probability between 0.25 to 0.5 of having crystallized in a garnet-bearing assemblage. But the probabilities are much higher for analyses of the rims of these grains. And so this really supports the interpretation that you might have already made based on the textural, the texture of the titanites, which is that what you're seeing here is titanite crystallization that spans across the interval of garnet growth. So you're both predating and post-dating the appearance of garnet. And so now when the uranium-lead data from the titanite in this sample yields a consistent uranium-lead age of 1163 million years, this basically tells you that this is coeval with the crystallization of garnet in this sample. Okay, and as for another example, let's have a look at this Mafic gneiss here. So titanite in this sample was mostly unzoned in backscatter electron images, or it had this very narrow, sharp rim, which you can just see in some of the images. However, two of the grains that were analysed, which are marked here in orange, were different. So these were partly recrystallized in backscatter electron images. Again, the different morphologies of the titanite correspond with different trace element compositions. So the main population of unzoned titanite had much flatter rare earth patterns, and the two partly recrystallized grains were more depleted in the rare earths overall. Now, you might have also noticed that in the top left of the thin section, there is a pink mineral, which of course is garnet. And as it turns out, titanite has an interesting spatial relationship with the distribution of garnet in this thin section, as you can see in the map here. And so most of the titanite in this sample is not actually in equilibrium with garnet. So you can see the titanite chemistry varies with the proximity to garnet on the millimeter scale. And so if we apply our logistic regression to the data from this sample, the blue dots are the data from the unzoned titanites. So these typically had quite a low probability of having crystallized in a garnet-bearing assemblage. But these probabilities increase from the core to the rim of the partly recrystallized grains, which are shown here in orange. So these data, together with the petrographic context, again, support an interpretation that most of the titanite in this sample belongs to an earlier metamorphic assemblage that did not contain garnet. But the mineral assemblage in the top part of the thin section is in the process of recrystallizing. And so associated with this, as the reaction front proceeds across the rock volume, you've had some partial recrystallization of some titanite in the sample, resulting in some heavy rare earth depletion. So what this tells us is that in this sample, the uranium-lead age derived from the unzoned titanite provides an upper constraint, age constraint that predates the appearance of garnet at this location. Okay, so let's talk about igneous and metamorphic titanite. So one thing I want to talk about here briefly before I actually get into that is just the classification system. And so this is probably relevant because there's a few papers, I've seen a few papers recently where people are starting to apply these kinds of statistical classification methods to large geological data sets. But one of the requirements of this approach is that your data has to fit into neat categories. But one of the challenges, of course, is that natural samples frequently are more complicated. So in our case, so in this one case here, where you might have an igneous titanite core with a metamorphic titanite rim, you've got to think carefully about what you're going to do with that, with the data from that sample. So when you have a simple igneous titanite, say in a granite, or a metamorphic titanite in some kind of a gneiss, that's pretty straightforward to classify. But as I mentioned, titanite is quite susceptible to recrystallization in metamorphic rocks. So there are in-between cases where perhaps you have an inherited igneous grain, which has a near-crystallized metamorphic rim. Or sometimes your precursor igneous titanite is recrystallized during metamorphism. So I really tried to separate out these scenarios from the pure igneous and metamorphic end members. And this will become relevant later. Okay, so where do we go from here? Well, the next step is to try to find some indicator elements that distinguish the categories of interest. And so for this, we're going to use the aluminium-iron ratio and the sum of the light rare earth elements. And so here's why these elements work. The aluminium-iron ratio is useful because although aluminium and iron both substitute for titanium in the crystal lattice, aluminium tends to be preferred at higher pressures because it has a smaller ionic radius. So broadly speaking, metamorphic titanite typically appears at sort of moderate pressures, so somewhere in the amphibole facies, whereas in igneous rocks, it tends to crystallize at much lower pressures. And so that's why you get a difference in aluminium-iron ratio between the two crystallization settings. In fact, aluminium-iron ratio has been previously proposed as a discriminator for igneous and metamorphic titanite, although I actually haven't seen this taken up widely in the literature, and we're not sure why that is. With regards to the light rare earth content, I think this may be related to the different sources of these elements in igneous versus metamorphic settings. So igneous titanite typically forms quite late in the crystallization sequence. By this time, incompatible elements such as the rare earths tend to be concentrated in the residual melt. And so when it crystallizes, igneous titanite can be very light rare earth rich. However, in contrast, during solid state metamorphism, the trace elements have to be sourced from metamorphic fluids, or they have to be released by the breakdown of precursor minerals. So if you've got trace elements, but they're bound up in stable mineral phases, they just simply won't be available for any newly crystallizing metamorphic titanite. And so hence, metamorphic titanite tends to have a much wider range in light rare earth content, but also has much lower light rare earth content overall. Okay, But the next question now is, where do you draw the boundary between these categories? So you can see that the two groups do differentiate on the cross plot. But if you wanted to actually create some kind of a classifier, you're going to have to draw a line at some point. So in the previous problem, when we were talking about identifying the signature of garnet in titanite, we had only a single variable. But here we've got two variables, so aluminium iron ratio and the sum of the light rare earths. And we're going to use an algorithm called a support vector matrix. So like the logistic regression, this is a classification algorithm, but it can handle nonlinear decision boundaries. So basically, the way it works is that you tell the algorithm what composition your data points have, so aluminium iron ratio or the light rare earth content, and then you tell it what your categories of interest are. So for example, igneous or metamorphic. And then it calculates the plane of the maximum separation between the groups, which is this boundary here. And so even though this is a fairly simple matrix, because there are only two groups, the benefit of this approach is that it really minimizes human bias, because I'm sure that you and I would probably draw the line in a different place. The other benefit is, as I previously mentioned, that you can use part of your data to define the boundary, and then you can use the remaining data to test how good the classifier is. So this classifier is pretty good overall. It correctly identified 89% of igneous and 87% of metamorphic titanites from the test data set. I just want to briefly mention here that we also looked at the thorium-uranium ratios, but I just found that it didn't do a good job of discriminating between categories. And I mentioned this because I've seen a few examples in the literature where metamorphic titanite has lower thorium-uranium ratios than igneous titanite. And people in some studies have actually tried to use this as a discriminant between igneous and metamorphic titanite. However, when we look at the compilation, a third of metamorphic titanites have a high thorium-uranium ratio, and they actually can't be distinguished on that basis alone from an igneous titanite. So what's the reason for this? Well, in fact, if we look at this again, we find that the thorium-uranium ratios are actually distributed differently according to metamorphic grades. So titanites from low temperature or higher pressure rocks have lower thorium-uranium ratios. And titanites from granulites and UHT rocks, so higher geothermal gradients, these have a much wider range of thorium-uranium ratios, but also have higher thorium-uranium ratios overall. So if you just have an unknown detrital titanite, thorium-uranium ratio is just not a good indicator to tell you what the origin of that titanite is. But it is useful in one particular case, which is when you have both inherited igneous titanite and metamorphic titanite in the same rock. So here are a few examples from the literature where you have inherited igneous grains that have high thorium-uranium ratios. These are the data points in orange, compared with the recrystallized or the neocrystallized metamorphic titanites, which are in green. And this is probably because the fact that you've preserved your inherited igneous titanite in and of itself, this tells you that you've got a metamorphic history that was not hot enough to crystallize high thorium-uranium metamorphic titanite. Okay, so let's talk about the bulk rock composition. So for this, we categorized all the lithologies into four simple categories: felsic, mafic, calc-silicate, and paragneiss. And so using the same approach as with the igneous metamorphic classifier, so this support vector matrix, we found that the classifier was overall 89% successful on the test data set, which is really good. And so those titanites from felsic host rocks have higher iron content and lower zirconium-yttrium ratios. So the zirconium-yttrium ratio makes sense with experimental studies of titanite melt partition coefficients. And so these studies show that yttrium partitioning correlates with the composition of the melt. Temperature also plays a role in the yttrium partitioning. And so because we know that zirconium also correlates with the crystallization temperature, for a given temperature, an igneous titanite from a felsic rock tends to have a higher yttrium content and a lower zirconium-yttrium ratio than an igneous titanite from a mafic rock. Interestingly, we see the same distribution of zirconium and yttrium ratio for both metamorphic and igneous titanites So presumably the metamorphic felsic titanites inherit this from the parent bulk rock composition. As for the iron content, we actually don't really have a good understanding of what controls the iron content of titanite. As far as I'm aware, titanite melts iron distribution coefficients have only been measured for one bulk rock composition. But this is something that really just emerged empirically from the data, and it seems to work. The other thing I want to point out here is that if you know that you've already got an igneous titanite, so say you've applied the previous discrimination diagram, you can now basically distinguish felsic from a mafic igneous host rock composition. Okay, so let's put these classifiers to use and work through a couple of case studies. So this is a paper that was published in 2020 in Earth Science Reviews, where they analysed detrital zircon, titanite, rutile, and monazite from 3 tributaries of the Yarlung-Sanko River in Tibet. And we're just going to focus on what the titanite can tell us today. So the inset here is a topographical map of the Himalaya, with the Yarlung-Sanko running east-west in the middle here. And the catchment areas of the 3 tributaries are outlined in red, with the sample locations as the yellow dots. And you can see that the Pumchu and the Nyanchu rivers to the left primarily sample the Tethys Himalaya, which is in brown. And the Lhasa River up here to the east has a source region that's quite different from the Lhasa block. So based on this, you might expect that titanite from the Pumchu and the Nyanchu rivers is going to be geochronologically and chemically quite different to titanite from the Lhasa River. Now, one complication from this study is that they didn't analyze the complete suite of trace elements that we're interested in. And unfortunately, this is actually the case with most published analyses of detrital titanite. So in this case, they analyzed the rare earth content of the titanite and the thorium and the uranium, but they didn't analyze aluminium or iron. And so we can't apply the full discrimination diagrams. But in a qualitative sense, this is still a really nice example of how the trace element content can tell you about the provenance. So I showed you this earlier. This is from the large titanite compilation, light rare earth content according to different crystallization setting. And if we look at the data from the 3 rivers, we see that indeed they are quite different. So the Nyanchu and the Pumchu rivers in blue and green have a titanite signature that's a lot more similar to the metamorphic titanites, whereas the titanite from the Lhasa River has a much more igneous signature. If we look at the uranium-lead geochronology as well, we can see that the ages vary between the different rivers. So titanite from the Nyanchu and the Pumchu rivers has median age around 22 million years, and titanite from the Lhasa River is a bit older at around 48 million years with the median age. And this matches what we see of the source regions of the 2 rivers, the rivers as well. So this is a geological map of the catchment area to the Lhasa River. And the main thing to note here is that about a quarter of it consists of this red unit, which are gangues granodiorites of around 50 million years of age. So that's really a great fit with this sort of 48 million year titanite age and this dominantly igneous signature. This is also interesting because it really drives home the point about how accessory mineral fertility controls the detrital signature. So as you can see, detrital titanite from the Lhasa domain appears to be almost entirely sourced from these granodiorites, even though they only make up a quarter of the source region. And in contrast, if we look at the geological maps of the Nyanchu and the Pumchu catchment areas, these are mostly made up of sedimentary rocks, with a near absence of igneous rocks in the source areas here. And there is actually documented metamorphic titanite growth in the greater Himalaya domain in these source rocks between 10 to 30 million years. So this distribution of uranium-lead ages and the metamorphic titanite signature is consistent with what has been observed in the bedrocks. Okay, let's look at our last case study for today, which is titanite from sedimentary rocks of the Moine supergroup in Scotland. And let's see if we can say anything about the titanite in these rocks. And again, we're going to start with a geological map, this time in the Northern Highlands terrain of Scotland. So in pink is the Archean-Nilwausian gneiss, which has been thrust eastwards over the Moine supergroup here in cream and beige colours. And so the Moine supergroup is a 5 to 10 kilometre thick sedimentary sequence, which was deposited during the Neoproterozoic, and it was probably first metamorphosed shortly afterwards. And then it was further deformed several times after that, finally culminating in Caledonian orogenesis during the Silurian and the Ordovician. So in this study, the authors again analysed a suite of minerals: monazite, xenotime, titanite, zircon. But again, we're just going to focus on the titanite for today. So we're going to look at these samples here. 2 from the ΣΛΡΕE Nappe, 1 from the Nappe Nappe, and 3 from the Moine Nappe. And so this is what the uranium-lead geochronology of the titanite from these samples looks like. But the main question here is how to interpret these mineral ages. So which of these are neocrystallized metamorphic titanites and which are detrital minerals? And for the detrital grains, what can we say about the source lithologies? Okay, let's talk about the samples from the ΣΛΡΕE and the Nappe Nappes first, because they're a little bit simpler. And if we look at the Igneous metamorphic classifier, we see they all plot within the metamorphic field. And this actually makes sense given that the uranium-lead ages of the titanites are mostly Caledonian. So these are much younger than the age of deposition. So you might expect that these are in fact metamorphic. Both of the samples from the ΣΛΡΕE Nappe, which is in orange and yellow here, plot within the non-felsic field of the composition classifier. However, titanite from this sample in the Nappe Nappe plots across the boundary, so sort of from non-felsic through to felsic compositions. And this actually makes sense, given that in the larger titanite compilation, data from the paraneizers does tend to plot right here on the boundary. So those are the purple points here. Interestingly, actually, if we look just again at this sample from the Nappe Nappe, we see there's a striking difference in iron content between the older, slightly older titanite cores, which have a lower iron content and some age inheritance, and the titanite rims, which are slightly younger in age, have a higher iron content and don't have any of that evidence of age inheritance. And so here, it's possible that the changing iron content actually represents growth in a changing metamorphic assemblage. But as far as we can see from the logistic regression for the garnet signature in titanite, most titanites from these samples probably crystallized in garnet-free assemblages, which again makes sense because there's no garnet described for any of the 3 samples. Okay, so now let's talk about the data from the Moine Nappe, which is a little bit more complicated. So the titanites from these samples mostly have pre-Cambrian ages, with some evidence for younger overprinting. Now, we can already see from the geochronology that some of the titanites must be detrital because they have uranium-lead ages that are older than the age of the deposition of the sediment. And we can see with the igneous metamorphic classifier here that the samples mostly plot in the metamorphic field, with some analyses crossing over into the igneous field. But interestingly, particularly if we look just at the MTA and the MTB samples, there's a trend with the uranium-lead age where the older samples that have more age inheritance plot closer to the igneous field and the younger samples plot more in the metamorphic field. So to understand this, let's just go back to the larger titanite compilation for a second. So the igneous samples plot at high light rare earth content, low aluminium iron ratio, but the inherited igneous titanites, so that's igneous titanites in rocks that are overprinted by metamorphism, these start to trend down towards the metamorphic field, like this. So based on this, I'd suggest that actually what we're seeing here is that some of these Moine Nappe titanites are actually detrital igneous titanites with some evidence of a metamorphic overprint. Okay, so now if we look at the composition classifier, we see that the 3 samples again plot across the boundary from felsic to non-felsic compositions. MTC, which is this black sample here, mostly plots on the non-felsic side of the boundary, whereas the other 2 samples are kind of split evenly across that. But if we look just at those other 2 samples, again, we see there's this correlation with age, where the older titanites plot more in the felsic field, and those which record younger ages plot across into the non-felsic field. Okay, so now let's put this information about the crystallization environment and the source rock composition together. And so we can see that there's a few different source rocks likely here. So first, this older group of inherited titanites probably crystallized in a felsic igneous rock. A lot of these pink grains here, these plot really close to the igneous metamorphic boundary, which is consistent with the effects of overprinting metamorphism. And then finally, this group of the younger titanites probably crystallized in a metamorphic rock. So based on their ages, these are also probably detrital titanites. And actually, if we look at the logistic regression for the garnet signature in titanite, again, most of the titanites from all three samples probably crystallized in garnet-free assemblages. And so this is interesting because samples MTA and MTB both contain garnet as part of the metamorphic assemblage, but we don't see evidence of the garnet crystallization signature in the titanite. So this is just another independent line of evidence, in addition to the geochronology, that supports a detrital origin for the titanite in these samples. So I think this is pretty cool because we've been able to basically use the titanite chemistry to identify two different potential source rock lithologies for detrital titanite in these samples from the Moine Nappe. So as you can see, we can get a whole lot more information out of the titanites just by incorporating the data from the trace element chemistry. Okay, so let's just briefly revisit the two hypothetical scenarios I showed you at the beginning. And today I've shown you some tools that can help you to interpret your data in either of those two cases, whether you're taking a petrochronological approach or whether you've got detrital titanite from an unknown source provenance. So the three classifiers I talked about today are the logistic regression for the garnet signature in titanite, the igneous metamorphic classifier, and the felsic composition classifier. And this kind of analytical approach could actually be applied to different data sets of different accessory minerals, not just titanite. But if you are working on titanite, you can read more about this in this recent paper in Terra Nova. And that's all I've got for you. Thank you.
Okay. So do we go?
Yeah, I think remove spotlight.
Remove spotlight. Okay. Thank you, Elisabeth. It's always hard on these Zoom meetings to understand how much applause you got, but you got applause in the room from us. We can't hear it. And I think you got applause online as well. So thank you. That was a really interesting talk. We've got a question here from Mav.
Yes. Thanks for the talk. That's fascinating. And I have a few questions. One of them is something people I'm sure are asking you quite often is about the closure temperature. So could you talk about that? Because it appears sometimes like it gets quite easily reset at reasonable temperatures.
Yeah, that's a good question. And I would say that's a whole can of worms that I just didn't talk about here. Basically, I would summarize it as follows. So lab experiments where people have tried to look at the closure temperature of lead in titanite tend to put it sort of around 650 degrees, 550, 650 degrees Celsius. But there are numerous examples of natural titanite in the field where it's been able to survive up to 850 degree granulite fascious metamorphism while retaining age information from a previous metamorphic event. And so basically there's this discrepancy between lab studies and natural studies of the lead closure temperature. I'm not sure that there's, I'm not sure what the solution of that, what the solution of that is. My hunch is that maybe it has something to do with fluids, because I know in other minerals we also see, you can see age inheritance beyond the nominal closure temperature, particularly in fluid absent systems. And so where we do see this age inheritance, it tends to be in terrains where there something strange is going on with the fluids. They tend to be very dry rocks, and you're just not recrystallizing the metamorphic assemblage. And so conversely, if you've had a lot of fluids through the rock, titanite probably actually will recrystallize at quite low temperatures. And what you're getting there is not so much thermal resetting, but actually it's just recrystallizing. Does that make sense? Yeah.
So another question I had was on the fluid thing. it seems to be that a lot of folks think there are quite an abundance of hydrothermal Titanites, yet that wasn't a category in any of your stories. Is this because they're too messy, or?
To be honest, I collected data from there's a couple of papers where I had data from hydrothermal Titanites. It was a bit more messy. And then I had to sort of focus on something. Yeah.
Okay. And then my final question is, you showed a spidergram with a lot of trace elements on it. Yes. And I was wondering, is that the entirety of what you find in Titanite, or is that the entirety of what people looked for?
That's one particular study from 2002. So there are different studies where people have looked at different elements. So that's not the entirety of everything. Yeah.
So there's more. We could do the whole periodic table.
You could do the whole periodic table. Yeah. And I can see actually on that, so there's a question in the chat. Anthony's asking about niobium and tantalum in Titanite, and I didn't talk about that. And that's one of those examples where there was a few potentially interesting elements that I just couldn't look at, mostly because just not enough people had analyzed them. And so you sort of run into this issue where the more, so you've got the rare earths, and then maybe you want to add zirconium to that list, and you want to add aluminium and iron to that list, and then you add niobium and tantalum, and suddenly your data set's not representative anymore. And so manganese, interestingly, was another element that I thought looked super interesting. In that it looks like it had quite a good ability to discriminate certain host rock compositions. But because there was only about 6 papers that had analyzed manganese, you can't make any conclusions based on that. And so it was sort of the same with the niobium and the tantalum, where there just weren't enough studies. It wasn't a representative data set.
Okay, thanks.
Thank you. And Elisabeth, you can probably see that there's a question from Michael in the chat. Would you like me to read it to you, or?
Yeah, sure. Yep.
Michael is saying Titanites can have heaps of rare earth elements, and in some ore deposits, those light rare earth elements actually reach weight percent levels. Would the Henry-like partitioning behavior, so straight line behavior, affect the partitioning along the rare earth element series and shift that ratio of light rare earth elements to heavy rare earth element ratios?
To be honest, I don't really know. I've not looked at I've not really looked at any data from ore deposits or anything with such unique compositions as being sort of at the weight percent level. And so, the behavior might be different. And something like that, I guess, when you're dealing with something more as a major rather than a trace phase. Yeah, I'm not sure.
Yeah. And a question now popping up in the chat from Anthony. He's asking, any advice on analysing iron, especially with laser ablation, ICP-MS? At least in our lab, the background goes up and down during the course of the day, and they get inconsistent. What is an RSF on something like MIST 610?
So I don't know. I mean, I guess we've not found that issue. I know, so we usually will measure both iron 56 and iron 57, and one of them tends to do better than the other. But I've not really noticed that particular issue. I guess we usually, after we turn the laser on, we let it run for a couple of hours while the background sort of decreases to acceptable levels. So, I'm not sure.
John has a follow-up question, I think.
Yeah, so when you showed the partitioning into Titanite, you spoke of alumina and iron 3+ going in for the 4+. How do you suppose that's balanced?
Yeah, so that's there's been a couple of papers on that back in, I think, the 90s. That's usually balanced by coupled substitution of a hydroxy ion, or sometimes can be fluorine as well, I think. And so The fluorine hydroxy ratio is also quite dependent on obviously the availability of those elements, but also fluid composition and also metamorphic grade. So there's a few other complicating factors there, which is part of why you actually can't use the aluminium content as a geobarometer in titanite on its own. But
Okay.
Yeah.
Thanks.
Yeah.
Awesome. Yeah, Anthony's saying Uli Troitz wrote a paper about fluorine-bearing titanite, and I'm standing here actually laughing with Sarah because I wrote one 10 years ago and I don't remember what I wrote.
Maybe Elizabeth's read it and remembers.
But we found a green and a brown titanite in the same rock, and they were huge, and we analysed them for the ferric ferrous and cerium was actually in different concentrations too. So that might be an interesting follow-up as well.
So there's a couple more questions in the chat, but it's 5 p.m. so we might end it here and suggest that people send you an email if they've got more follow-up questions. But thanks again for a really interesting talk. That was, as someone who doesn't study this at all, I